I would like to welcome you to project video 1 of 2 for electrical engineering to FH3. Today we'll be talking about the dielectric resonator antenna. We are group B26. What is an antenna? An antenna is a device responsible for converting electrical power into radio waves, or radio waves into electrical power. They utilize radio transmitters and radio receivers in this process. There are two phases of this process, transmission and reception. In transmission, an electric AC current signal oscillating at a desired frequency is forced through the antenna. This oscillating AC signal oscillates electrons, which radiates the energy as transverse electromagnetic waves, containing both magnetic field and electric field components. In reception, the antenna detects the electromagnetic waves in the air, and the oscillations of the wave move electrons in the antenna. Power picked up by the electromagnetic waves is used to create a voltage. This voltage can be sent to a radio receiver to be amplified and processed.
DRA history. Previously, dielectric resonators had been mainly used within microwave circuits like oscillators and filters, and they were mainly used for energy storage applications. In the early 1980s, Professor S.A. Leung proposed a paper on dielectric resonators that showed that they could be effective radiators. This led to the idea to use a dielectric resonator as an antenna. The reason for this innovation was a result of the inefficiencies of metallic antennas like the microstrip antenna. At that point in time, wireless communications devices were beginning to use higher frequency ranges. At these higher frequencies, metallic antennas began to experience a large drop in efficiency as a result of conductor loss. When looking at the losses from a dielectric resonator antenna, it can be shown that the main loss is caused by imperfections in the dielectric material used. This loss is very minimal compared to the metallic antenna losses. Some other advantages include the small size, low cost, good bandwidth, and easy excitation, as explained in other slides. The dielectric resonator antennas and metallic antennas shared many attributes, which is the reason why the DRAs were a good replacement option to the metallic antennas. One of the first dielectric resonator antenna was a cylindrical DRA proposed by Leung. There are many different types of DRAs now. For example, the 3D transparent models that are now used for aesthetics, like the glass swan you see here.
How does a DRA work? When an electromagnetic wave hits the dielectric resonator, the sudden change in permittivity causes the wave to be trapped inside of it. The wave bounces back and forth within the resonator at certain frequencies called resonant frequencies, which are determined by the DRA's physical dimensions and dielectric constant. DRAs are the optimal choice for microwaves, which have a bandwidth of close to 300 GHz, from 0.3 to 300 GHz. At these wavelengths, antennas utilizing metal structures become very inefficient due to high internal losses.
Like many areas of electromagnetics, the area of dielectric resonator antennas is rapidly expanding. One of the main areas of research is in the area of different geometries and their specific applications.
The dielectric resonator antenna has many different structures and designs because it is so versatile with its small size, lightweight, higher radiation efficiency, wider bandwidth, and low cost. DRA designs include a dielectric material with a low permittivity to enhance radiation. The DRA also has a low loss, which only comes from the imperfect dielectric material used and no conductor loss. The DRA has many different structures, including cylindrical, rectangular, hemispherical, low-profile circular disc, low-profile triangular, and spherical cap, to name a few. One structure of the DRA is the cylinder. This was actually the first DRA that was designed, which led to investigations of other structures. The cylindrical DRA uses a constant diameter but varies in height, dielectric constant, position of the probe, and length of the probe. For the cylindrical DRA, the degrees of freedom are limited to only one. The cylindrical DRA is mounted on a ground plane.
Here are the magnetic and electric field equations for a cylindrical DRA. If we cross the electric field with its normal, pointing out of the DRA surface, we get the magnetic field. This picture is a diagram of an ideal far field radiation pattern of an infinite ground plane for the TM01.
The hemisphere is another geometry used in the structure of DRAs. This is again mounted on a ground plane. The hemispherical DRA has an advantage over the rectangular and cylindrical shapes. This is that the interface between the dielectric and air is simpler. However, a disadvantage that the hemispherical DRA has is that it does not contain any degrees of freedom.
Green's field function. Green's field function single mode approximation is to solve non-homogeneous boundary value problems. J hat is the spherical Bessel function solution to Laplace equations in cylindrical coordinates. H hat is the Hankel function, the Bessel functions with imaginary numbers. By getting the Green's field, you can get the electric field with respect to the probe.
Another main DRA structure is the rectangle. Such a simple geometry has many benefits. This particular shape is the most versatile because it has 2 degrees of freedom. This means that for a given resonant frequency and fixed dielectric constant, 2 of the 3 dimensions can be chosen independently. Rectangular DRAs also provide a very wideband frequency response. These DRAs are also mounted on a ground plane.
These are the electric field equations.
Other structures of DRAs are low-profile ones. These designs differ from regular DRA structures in that their height is significantly reduced, basically resembling more of a flat surface. Low-profile DRAs have many use in common modern applications. One application of a low-profile DRA is in a notepad computer connected to a wireless network.
Excitation. There are multiple excitation methods for DRAs, including the use of a coaxial probe, aperture coupling with a microstrip or coaxial feed line, direct microstrip feed line, coplanar feed line, slot line, and strip line. And here you can see 2 pictures, one showing a coaxial probe DRA and one showing one with an aperture coupling. The size of a DRA is in the order of lambda over square root of ER, where lambda is equal to the wavelength and ER is the dielectric constant of the dielectric used. There are 2 fundamental antenna types, which are omnidirectional antennas, which transmit and receive radio waves in all directions, and directional antennas, which transmit and receive radio waves from one direction only. There are 3 types of modes. Transverse electric, TE, where no electric field is in the propagation direction. Transverse magnetic, TM, where no magnetic field is in the propagation direction. And hybrid electromagnetic, HEM, where electric and magnetic fields are in the direction of propagation. Transverse modes occur because of boundary conditions that the waveguide imposes. Solving Maxwell's equations using the specific boundary conditions allows us to find out what the allowed modes are. Different modes give off different radiation patterns, which can satisfy different coverage requirements. There are hundreds of different DRA shapes and sizes. Each have unique equations describing their resonant frequencies. The resonant frequency of the NPM mode for a cylindrical DRA can be calculated using the following equation. The fundamental mode, which has the lowest resonant frequency for the cylindrical DRA, is the TM110 mode, where the resonant frequency is given by this equation. Notice that changing the dielectric material reduces the resonant frequency.
When designing a dielectric resonator antenna, one of the most important things you have to consider is what type of dielectric material you want to use. So what is a dielectric material? A dielectric material is an insulator that becomes polarized in an electric field. So this means that while no current can go through it, there is an electric field. The one difference, though, is that the internal electric field is not necessarily the same as the external electric field. So difference between dielectrics. This will help understand why you may choose one dielectric over another in your design. So the electric susceptibility, Xe, is related to how easily the material polarizes. Epsilon r is equal to your electric susceptibility plus 1, and your electric flux density is equal to your epsilon r epsilon naught times your electric field. The higher your epsilon r is, the denser the induced electric field will be. Here's a list of some common dielectrics you may come across. The most popular that I have found through research is air and glass.
So here are some advantages and disadvantages of the DRA. DRAs are inexpensive, they can be very small and lightweight, they have very low power loss due to their use of dielectrics rather than lossy materials like metals. This makes them highly efficient. Efficient antennas will radiate most of the power present at their input away, whereas an inefficient antenna will have a lot of its input power absorbed as losses within the antenna. As a formal measure, efficiency is equal to power radiated divided by power at the input. Some disadvantages are that DRAs are sensitive to mechanical vibration and temperature variation, and there are some difficulties in the fabrication involved in the cutting of the dielectrics, both for shaping purposes and for the drilling of the feed line probe.
Now we're going to take a look at a specific geometry of a DRA, and this specific inverted U-shaped geometry is used for wireless local area networks. In the diagram on the left, the dark blue is actually the resonator, and the light blue is the grounding plate. The DRA has an area of 20 by 20 millimeters squared with a slot of 7 by 6.5 millimeters squared. And the rectangular patch in the inverted U dielectric resonator antenna is a feeding mechanism which feeds the current into the dielectric. The microstrip in gray that leads to the edge of the grounding plate has a resistance of 50 ohms, as well as this specific resonator antenna resonates at a frequency of 5.5 gigahertz. The return loss of this is found to be 22.7 decibels, and the return loss is defined by the loss of signal power resulting from the reflection caused by a discontinuity in a wave. The antenna radiates in the broadside direction as shown in the diagram on the right, and in conclusions, it was found to be effective for transmitting WLAN networks.
So for further research, in the next section of this research assignment, we will be looking into the use of multiple different dielectric resonators stacked on top of each other and their effect on increasing the bandwidth of the DRA. This concludes our video presentation. Please like, rate, comment, and subscribe for more videos. Thank you.